next award is the Arden L. Bement Jr. Award Lecture. And that award was established in 2015 to recognize a Purdue faculty member for outstanding accomplishments in pure and applied sciences and engineering. Professor Bement had a long and distinguished career with Purdue, serving as the Basil S. Turner Distinguished Professor of Electroceramics, the David A. Ross Distinguished Professor of Nuclear Engineering, and Purdue's Chief Global Affairs Officer, achieving international recognition as Director of the National Science Foundation and Director of the National Institutes of Standards and Technologies. He received a doctoral degree in metallurgical engineering, as well as 7 honorary degrees in science and engineering from universities around the world. Here to present the Arden L. Bement Jr. Lecture for 2024 is Dongyan Xu. Dr. Xu is the Samuel Conti Professor of Computer Science and Director of CERIAS, which is the Center for Education and Research in Information Assurance and Security. He's a leading authority in cybersecurity, and his pioneering research has advanced security frameworks for critical infrastructure and systems, including unmanned aerial systems, industrial control systems, and the Internet of Things and networks. His work has been widely recognized for its impact on national security and real-world application. Professor Xu's talk today is titled Cybersecurity in an Increasingly Cyber-Physical World. Join me in welcoming Dongyan.
Thank you so much, Karen, for the kind words and introduction, and thank you for your leadership and support through the years. And I would also like to thank my other bosses, Dan, Lucy, and a lot of my dear friends and colleagues who are in this room. I cannot do this without you. And it's always, I feel always proud to be an honor receiving this award named after Dr. Bement. And also, it's a privilege being part of the Purdue's research enterprise. And I would like to thank David for preparing our next generation for what I'm going to talk about. Seriously. So I'd like to share some of my experiences and observations on cybersecurity, especially in our increasing cyber-physical world. So we're looking at some of the photos of some of the real-world systems, a drone, a river dam, and also manufacturing machinery, and a smart bike trainer in the gym. So on appearance, these are just physical systems that are very different from our cyber system like PCs, laptops, smartphones, and servers. But if you look under the hood, you actually see a kind of a hidden cyber layer behind each of these systems. For example, the drone has a microcontroller embedded with sensors and connected through wireless to the ground control station. And the river dam has a whole bunch of sensors monitoring different parts of the dam and then sending data back to the central controller, which may also be connected to the internet. And then for the manufacturing machinery, it is typical to have a programmable logic controller, and then collecting and making control decisions in response to sensors, and also having a human operation station, all connected through what we call a OT or operational technology network. And this can also be connected further to the IT side of the same enterprise. And finally, if you look at the smart bike, we also have sensors throughout the bike, as well as the cyclist's body. And then all the real-time data gets collected and processed by a microcontroller, which will in turn transmit the data through the edge device to the cloud, for example, to a server that coordinates a virtual bike race. So all this actually shows the fusion between cyber and physical. So we call these systems cyber-physical systems, and the security about these systems is what we call cyber-physical security. So cyber-physical security is truly everywhere. So here we're looking at that smart bike example, and this is actually a true story that happened a few years ago, where we have a kind of a virtual bike race among multiple cyclists in different parts of the world, and one of them happens to be a software engineer. So he managed to hack into the embedded controller of his bike, and then he actually kind of made up some kind of a data for example, the ground speed, the rotational speed, the rotational rate, and he actually sent this fake data, right, through the internet towards the race server, giving himself some unfair advantage. So by the way, we're working very closely with our sports engineering center led by Dr. Monson to actually counter such cheating, which we also call cyber-physical doping. So this is a kind of the lighter side of it. And then we also argue that cyber-physical security is really national security. So here we're looking at another real-world incident where that actually happened in 2016, where hackers, adversaries, kind of infiltrate into Ukraine's power grid through the internet, and leading to a national level power outage. And coincidentally, in the same year, we actually experienced kind of a different type of cyber physical attack here in the US, where adversaries first infiltrated into tens of thousands of IoT devices like our cameras, sensors, home appliances. And these devices actually launch a DDoS or denial of service attack against some of the major internet infrastructures, actually bringing down servers such as Amazon and Netflix. Imagine your coffee maker is part of an attack that brought down the internet, right? And then more recently, we also saw the ransomware attack against the Colonial Pipeline system, causing a gas price hike in certain parts of our country. So all these examples actually show that cyber physical security or threats against cyber physical system security is real, and we need to actually do some serious research about it. And then in the past decade, our own experience and also work being done in the community actually show two distinct camps of research or solutions. And one is what we call the physics-centric approach, and the other one is the cyber-centric approach. These two camps, they both try to address cyber-physical security, but from different angle. For example, the physics-centric approach, they tend to look at the system from a control and system perspective, and the cyber camp looked at the problem from a software, hardware, and network perspective. So we actually observe a gap between these two camps as well as the solutions produced by them. And what we would like to see is a kind of a closer connection and synergy between the two. Like a brief example, if you are trying to understand an autonomous vehicle like a drone, on the physics side, you want to do system identification to derive the system or the vehicle dynamics, parameters, and property. And on the cyber side, you want to understand the implementation of the control program and how, what is exactly the control logic and semantics. So in response to that, in order to narrow the gap, we have been developing, instantiating, and advocating an integrated cyber physical methodology for system security assessment and vetting, meaning that we want to proactively identify the vulnerabilities that exist in the system as well as possible attacks against that proactively before the adversaries do. So this methodology has 4 key steps. The first step is what we call the component level vetting. So we look at individual components or processes within the larger system. So here, on the physical plane, you are looking at the control models of a drone on the left and a chemical reactor on the right. And down at the cyber plane of the same component, you actually see the hardware and software that implement and execute these control models. So what we have been doing is to try to establish a mapping between the model and the program. So for the program, for example, you actually see different parts of the code implementing different aspects of the control. So this happens to the drone and to the manufacturing process. And further, we're able to establish the variables, for example, variables in the program, and we are able to map them back to the control model's input, output, state references, etc. So with this cyber physical model program mapping, we will be able to further, kind of in a goal-oriented way, analyze and discover the possible vulnerabilities and exploits against that. So here on the cyber, again, based on the mapping that was established. On the physical plane, what we are trying to do is to start from the possible attack goal, which is represented by a specific state of the control. And the problem is really how can the adversary maliciously steer the system from the initial state towards the attack goal. So this is actually a natural, very naturally translated into the reachability problem. So, but of course in a malicious kind of context. And so if you look at the cyber physical kind of interaction, there are multiple options to actually achieve that goal. So the first one is to corrupt the control logic itself, and this can actually be done possibly by a seemingly harmless USB drive with a piece of malware that got injected into the control code. And also, as another option, one might also be able to manipulate the sensor input. And this is typically done by creating some external disturbances, towards the sensor. There are reports where you can actually use a loudspeaker to actually affect the sensing capability of a drone and many other external disturbances. And yet one more possibility is to directly manipulate the actuation output. And this can be done by the adversary remotely connecting to the microcontroller and override the actuation output of the control program. So with a combination of such exploits, we are able to predict that adversaries be able to kind of steer the system from the current state toward the attack goal. So this is what we call the vulnerability and exploit discovery at the component level. And then the next step, once we understand the individual components and processes, we are ready to apply a similar kind of a method to analyze the entire system. So here we're looking at a kind of a hypothetical factory that makes drones. And you will see that there are typical components, including the power supply, the HVAC, the actual manufacturing, and then the product assembly. So ultimate with the product being a drone. So we performed a similar kind of a layering and mapping study. So you will see on the cyber plane, we're able to map out the corresponding cyber components that support these physical operations, such as a power controller, the 3D printing controller, the HVAC controller, and the assembly, et cetera, et cetera. In addition, you also see their network connectivity. They may be connected using different network, wireless, CAN bus, others, and also the dependency as well as their physical location. So you will see why the physical location actually matter in just a minute. So with this kind of a mapping, we are able to establish a kind of a cyber physical model for the entire system. And based on the mapping, we are again starting a kind of a goal-oriented analysis, meaning that I want to see if a specific attack goal can be reached, based on what we have here. So based on this cyber physical model and mapping, we develop algorithms to actually compute all kinds of possible plots that will achieve the attack goal. So hypothetically, let's assume that the goal is to disrupt the drone manufacturing supply chain. For example, by introducing drones with defective blades, propeller blades. So one possible plot generated by our algorithm is to first disrupt the 3D printing process that make the blades, right? So that the blades have some defects. And in order to disrupt the 3D printing process, one could possibly disrupt the power transformation and transmission towards the 3D printer. And then remember the component level analysis that we have done earlier. So here we can actually go down to the cyber plane to actually analyze what kinds of vulnerabilities that exist in the cyber plane that is able to realize such manipulation. And similarly, we do the same analysis for the 3D printing control. So down at the cyber plane, we will be able to run another set of algorithm to determine the end-to-end attack path to realize such a plot, right? So more specifically, suppose we have the power controller and the 3D printing controller within a kind of a heavily guarded, restricted area, meaning that adversaries will not be able to physically access these devices. So what can we do in order to actually launch the attack? So now you realize that the location of these individual components comes to the rescue, because we actually realize a seemingly kind of an obscure location, which is the HVAC control room. So in that control room, there is this operator station that is connected to both the power controller and the 3D printing controller, and it is actually physically accessible to the adversary. So this actually becomes the launching pad of this end-to-end attack. So let me kind of quickly illustrate the end-to-end plot that is generated kind of in a semi-automatic way by this framework. So the first step is to have the operator station. The adversary will inject a malicious actuation command to disrupt the operation of the power supply. So the power transformation and transmission will be anomalous and causing the 3D printing anomaly. And at the same time, the adversary will also inject fake normal sensing data to actually cover up this printing anomaly, meaning that the printing is not going right, but at the same time, the sensor keep reporting normal operation. So this means that the programmable controller will not be able to detect the printing anomaly, leading to the manufacturing of defective blades, and the blades get installed as assembled into the final product. So this is what we call the cyber physical exploit chain generation, meaning that based on the individual components and processes, we're able to chain together the vulnerabilities and exploits proactively again before the adversaries do so. So in the interest of time, I'm only talking about the vetting process, the vetting part of the security analysis. There are similar methodology for the hardening and recovery or mitigation of such vulnerabilities. Again, following the same cyber physical layering and the mapping methodology. So what we are currently working on are two parallel efforts. The first one is to develop destruction-oriented digital twins. We develop these twins for the sake of breaking them or damaging them, right? Again and again within a very short period of time. To achieve safety, meaning that we're not using the real physical system to construct these attacks. Efficiency, we're able to run tens of thousands of testing runs within just a few seconds. And fidelity, meaning that the vulnerabilities and exploits that we discover will also be valid within the real system. And at the same time, we're developing intelligent AI agents for performing the four-step analysis methodology, because right now, without the AI agent, the process that I described still take non-trivial amount of time and effort for the human investigator. So in the future, we will be able to train these AI agents with deep learning and large language models so that they become equally and even more skillful and knowledgeable, so that we can outscale, outspeed, and outwit the adversary. So the takeaway of my presentation, cyber physical fusion is happening, and cyber physical security is national security. And we see the gap between the cyber and the physical research, and a cross-layer or cross-plane methodology is a promising approach to actually narrow the gap. So that's the end of my talk. Thank you so much for your attention and support.
It's really wonderful that you bring so much knowledge in a way that we can understand.
Thank you, Jay.
The question I have is how this could be embedded into learning in all different disciplines, and not just engineering and science, but security of the cybersecurity is important for all and should be part of learning in all disciplines. Do you have thoughts on how one could embed it across curricula?
Absolutely. So this is a great point, Jay. So this is also what we are trying to do. We try to embed ourselves in different science and engineering disciplines, because we believe that cybersecurity should not be done within its own silo. as I mentioned earlier, we have all these real-world physical systems that have increasingly, equipped with cyber components. So we would like to actually offer hands-on experience to our students, not only in the traditional computing discipline, but also in other science and engineering discipline, so that they have a level of awareness and knowledge about that, and be able to work closely with folks in cyber. So we are doing this not only in our research as reflected in what I just reported, but also in some of the curriculums and the capstone student projects that we're conducting right now. Thank you.
This problem is so vast. I wondered how much can you use the drone example or some other example to standardize across different cyber physical systems, because I don't know otherwise how you get a handle on it. There's so many places.
Yeah.
Is there some standardization you can do, or does it have to be custom built for each manufacturing operation or drone or whatever?
That's another great question. And so we do see a lot of kind of a common insights and steps that are needed for a generic framework. And at the same time, it is true that we need customization and specialization when we are looking at a specific application domain. So I would say that a framework needs to be generic, but at the same time needs to be customizable, meaning that for different disciplines, we do want to work very closely with domain experts so that we can actually understand the specific challenges, domain-specific challenges, and then kind of get that into the framework. Thank you.
Okay, with that, let's give Dongyan a round of applause.